Hello, this video is going to be dealing with the same rock that we used an example for gravitationally stored energy. And we're going to talk about energy in falling objects specifically. We're going to assume that this falling object falls all on its own. We are not adding any additional energy into the system. It's not like somebody's coming in and that keeps hitting the rock as it's falling. We are also going to assume that there is no significant amount of energy that is converted into thermal energy. None is going to be stored thermally as this rock is falling, at least not enough to significantly change these numbers anyhow. So if we do have an object that is falling, right, there is several different positions we could measure. This one I just happened to kind of break it into fourths. You know, the overall height is 40 meters, so there'd be 1/4, half, 3/4, you know, the total height of the object. And we dropped it and we found the gravitational potential energy at these 5 different positions. All of the energy is gravitationally stored energy at the top, which is 19,600 joules. And right as it hits the ground, so we're going to say as it hits means that really the height is 0, it is just ready to hit the ground. It's not hit the ground yet, so it's not after it hits the ground, but it's right as it hits the ground. We're going to assume that the gravitationally stored energy is 0. So here is the question. Where did all of this gravitationally stored energy go that was initially in this object? Now, one answer could be yes, that it did go into thermal energy, and after it hits and the rock stops, that is where the energy would go. I mean, once again, if depending upon what it hits, there might be a little bit of sound energy or something like that, where the energy is transformed into. But we're looking at it just as it's hitting the ground right before that happens. So hopefully the answer is kind of obvious to you, that as soon as you let go of this rock, it starts moving. So as soon as it starts moving, then the energy is kinetically stored. So at the very top, if we have the 19,600 joules, sorry, I'm covering up the number, of gravitationally stored energy here, and at this position there's only 14,700 joules of gravitationally stored energy, some of that energy looks like it's missing. And so then the question is, how much is that? What is the exact number? So if I do a little bit of quick math here, I believe that answer is going to be 4,900 joules. Let me just check it out with the calculator quickly. There you go, if I could get it to turn on. And yes, it's 4,900 joules of energy. So we had 4,900 joules of energy that was gravitationally stored that isn't gravitationally stored anymore. And the reason is because now that is kinetically stored. So right at this position, I can say the gravitationally stored energy is the 14,700 joules, but the kinetically stored energy is 4,900 joules. That energy that is no longer gravitationally stored that we had at the beginning, because it's not as high as it was. If we go back up to the very top, I've written the mass number up there, but we can just kind of write this off to the side. The gravitationally stored was all 19,600 joules, and the kinetically stored energy is 0. At that point, it was not yet moving. All right, and we can just work on that all the way down. Here we said the gravitationally stored energy was 9,800 joules. The total still has to be the 19,600. I did kind of maybe blow by that point, right? If we start with 19,600 joules of gravitationally stored energy, that is the total energy in this rock throughout the entire interaction of it falling all of the way down. The total amount of energy has to remain constant. Right, so that's why I subtracted here. I had the total energy minus the gravitationally stored energy at this point will tell me how much kinetic energy there is at that point. And we can do the same thing here. We take the total amount of energy. We don't look at the total amount from the position before. The total amount of energy in the entire system is the 19,600 joules. We subtract the gravitationally stored energy amount at that point, and we will end up now with the total amount of energy at this point, which is kinetic. And if we look now, these two numbers match, which maybe should make sense. Because if we start at the top and now are halfway down, halfway to the bottom, we should have half of the gravitational energy that we started with, and then the other half should be kinetically stored energy, right? So these should be half and half. Each of these should be one half of the original. And that will always work. Once again, if this is just a falling object with no additional energy being added into the system from the surroundings, and if there's no energy leaving the system as thermal energy or some other form of energy, this kind of pattern should keep working. Halfway down, half of the original total amount of energy will be gravitationally stored energy. The other half will be kinetically stored energy. At this point, write this underneath, maybe a little more room. We have 4,900 joules of energy, which is gravitationally stored. And once again, we'll subtract. It'll actually be kind of the opposite math problem of the one at the 30 meters. We have 19,600 joules of total energy minus the 4,900 joules that are still gravitationally stored will give us the 14,700 joules, which are now kinetically stored. So the EK down here is 14,700 joules. Once again, our total of all of these is going to be that 19,600 we started with. And we get right to the very bottom where the gravitationally stored energy is 0. All of the initial energy, all 19,600 joules of it, are now kinetically stored energy. So for falling objects, this is kind of the pattern, and this is how it works. The easiest one, as long as you know the heights, should be to calculate how much gravitationally stored energy there is at these positions. If you subtract the gravitationally stored amount at each position from the total energy that we started with, you should always be able to find the kinetic energy. I know there were some examples like this on a couple of different assessments, and people got really confused because they couldn't calculate the kinetic energy because they didn't have a velocity. Well, using this sort of treatment, we don't need to know the velocity. We just need to know the total amount of energy at the beginning and the amount of gravitationally stored energy at each position. Do a quick subtraction, and that will tell us how much of the energy has been transformed into kinetically stored energy. This process could work in reverse also. I could have given you the velocity at each of these positions and had you calculate the kinetic energy, and from that you could work backwards and find out how much gravitationally stored energy there is. These problems will work in both ways. There is a separate video on how to calculate kinetic energy using the formula, and that one is just called kinetically stored energy calculations. So thank you for watching.